Hi everyone, welcome to this video where today we're talking about compound inequalities. Now, a compound inequality is just like a compound sentence. You learned in your English and language arts classes that a compound sentence is when you take two sentences and you put them together. And you have for, and, nor, but, or, yet, or so as all of the words that you could combine two sentences together to make a compound sentence. But here for compound inequalities, we're going to use two of those words, and or. So when you have a compound inequality and you put two inequalities together with and or, it's all about what numbers make a true statement when you plug them in, okay? And that's going to really be what the solution of a compound inequality is going to look like, where it has to meet both requirements or it could just meet one of the requirements. So I'm going to walk you through the three different cases of or, and then I'm going to walk you through the three different cases of and. So let's take a look. So first of all, an or, scenario number one. So if I said to you x is less than 4 or x is greater than or equal to 6, here's what that would look like. X is less than 4 would be an open circle shaded to the left because that's where all the values are less than 4. X is greater than or equal to 6 is a closed circle at 6 with everything shaded to the right. Now, if I said to you, you can pick any number in the world and it's got to either be less than 4 or greater than or equal to 6, you have a lot of options. Because if I say or, the number you pick just has to meet one of those requirements. You might pick a number that doesn't meet either one of those requirements, like 5, and you'll notice that 5 is not in a shaded region for either one of these. And 4 actually also would be a number that's not going to meet both requirements, or either requirements rather, because it's not less than 4 or greater than or equal to 6. The compound inequality for this would simply be me showing that both of these inequalities, these separate inequalities, are graphed on the same number line. So all the numbers that are less than 4 and all the numbers that are greater than or equal to 6. In set builder notation, the way we notate this compound inequality is we simply do open brace, x, that vertical bar. That means the set of all x such that. And then we actually just list both of them. So x is less than 4 or x is greater than or equal to 6. So this is the very first type of or situation that we could have. So let's take a look at this problem here. I'm just going to shift over. To get a discount at the diner, you must be either less than 10 years old, so you get like the kids rate, or at least 55 years old. So the two inequalities that are set up here, less than 10 or at least 55. Remember, at least 55 is going to mean greater than or equal to. So now if I was to create a number line, and an appropriate number line would be a number line where I have 10 on it, I've got 55 on it, and I go to graph both of those inequalities, my graph would look like this. And because they're completely separate from each other, in my set builder notation, I actually just list them separate from each other. There's no special way to write it other than just plug it into that set builder notation. Let's look at another one. You may be in a medical emergency if your heart rate is less than 40 beats per minute or higher than 100 beats per minute. So less than 40 or greater than 100. If I make an appropriate number line with 40 and 100 on that number line, everything less than 40, everything greater than 100. So any number that meets either one of those requirements would be in my solution. And that's what my set builder notation would look like. X is less than 40 or X is greater than 100. So now, that's the first kind of or scenario we can have. There's a second scenario. So what if I said to you X is greater than or equal to 4? That's what that graph would look like. Or X is greater than 6. Now notice these graphs actually are heading in the same direction. The previous graphs were always going in opposite directions. So now this is an or where if I said to you, you have to pick a number that's greater than or equal to 4, or the number has to be greater than 6. Now, when I say or, the number you would pick doesn't have to meet both requirements. It just has to meet either requirement. So if I took these two separate graphs and I put them together on just one number line, you're going to see that the entire second graph of X is greater than 6 is actually just already overlapping the x is greater than or equal to 4. It's kind of like this x is greater than 6 just doesn't even matter because I'm already including all the values that are greater than 6 in this inequality of x is greater than or equal to 4. So in this case, when you have an or compound inequality and both graphs are facing in the same direction, in this case they're both heading right, then you only worry about the inequality that basically takes over the entire solution set. So it's just x is greater than or equal to 4. So I don't list both of them, I just list the one that basically includes all of my solution. Because the x is greater than 6 is kind of irrelevant, it doesn't matter. Okay, so we're going to take a look at a couple problems like that. It says, to get an A in this class, your next quiz grade needs to be at least an 80. So x is greater than or equal to 80, or it has to be above a 90. Now think about this. If I said to you guys, hey, on your next quiz, you need to get at least an 80 or above a 90, either one is going to get you an A, would you really worry about getting the 90? No, because as long as you get an 80, that's what matters. That's going to cover all of your possible solutions. If I graph both of these, least 80, so greater than or equal to 80, and greater than 90, you can see the greater than 90 is basically irrelevant because the greater than or equal to 80 takes up the entire solution set. Let's look at another one like that. For it to start snowing, the temperature needs to be less than or equal to 32 degrees or less than 30. So it's got to be less than or equal to 32 or less than 30. Now think about it. Since it's or, it just has to meet one of those requirements. And, if you have if you have a temperature that's less than or equal to 32, or it's got to be less than 30, that less than 30 is already included in everything that's less than or equal to 32. So it becomes irrelevant. And your graph really shows you, whichever is overlapping, that's the one that we basically just don't have to worry about for our solution. Okay, so I've got one last case for you, scenario number 3. So x is greater than 4, or x is less than or equal to 6, rather. So now look at this. So they're going in opposite directions like scenario 1 was. Scenario 2, they were going in the same direction. So now these are going in opposite directions, but there's actually some overlap, like in the middle. So look at this. If I put both of these graphs on this number line, the entire left-hand side of the graph is going to be filled in. The entire right-hand side of the graph is going to be filled in. The entire number line is going to be filled in. When you have an or and they're going in opposite directions and there's an overlap, that means every single number in the world is going to meet one of these requirements. So I want you to think of a number right now. Any number in the world. Do you have it? Your number is definitely greater than 4, or it's less than or equal to 6. If you say your answer is not, you're wrong. Okay? Any real number that you could ever think of in the world is either greater than 4 or it's less than or equal to 6. And remember, or doesn't mean it meets both requirements. It just means it has to meet one of those requirements. And so that is actually all real numbers. So what we're going to see here in this last set of examples here, and these sound so ridiculous, guys, so just go with me. I will eat any pizza as long as it has more than 2 toppings or it's got less than 4 toppings. And it has to meet one of those requirements. So think about if I went ahead and I made a graph that went along with that, greater than 2 or less than 4, you have that overlap. So technically, any amount of toppings in the world meets one of those requirements. If I say I want 3 toppings, it's greater than 2. If I say I only want 1 topping, that's less than 4. Any amount of toppings would fit. And of course, negative doesn't really work here for that number line because you're talking about an actual word problem. But it's going to be any of those possible real numbers. Your chances of winning a prize are great. If I say pick a number out of a hat, you win if the number is at least 7, so greater than or equal to 7, or less than 10. So again, this is the same kind of case. Any number in the world you can think of meets one of those requirements. It's going to be greater than or equal to 7, or it's going to be less than 10. Again, we don't have to meet both requirements. That's what or is about. It can either meet the first requirement or it can meet the second requirement. And so again, that's all real numbers. Good. Okay, so now the second part of this lesson is about compound inequalities with the word and. And is a little bit more particular, actually a lot more particular, because when you have an and compound inequality, that means you have to meet both requirements. You have to meet both requirements. So with two inequalities, your number, whatever you pick, has to make a true statement for both. In the previous part, the first part of this lesson, or just means it has to be true for one of them. It doesn't have to be true for both. So let's take a look. X is greater than 4. We know what that looks like. X is less than or equal to 6. So now if I say to you, you have to pick a number that's greater than 4 and less than or equal to 6. Okay, look what actually happens here. The overlap, and I wrote overlap here, the overlap of these graphs is what we care about. So I'm actually going to just draw this sketch of the graph and show you if I was to take this sketch of the graph and actually just drag it over, slide it down, and overlap it onto the other graph, you can see this section here, from this open circle to the closed circle, that's where you have that overlap region. That overlap region, you guys, is this. These are all the possible solutions that meet this compound inequality. It's all the numbers that are greater than 4, and they're also less than or equal to 6. So 4.5 meets both requirements. 5 meets both requirements. Even 6 meets both requirements. But 7 is not less than or equal to 6. So 7's in the non-shaded region. So now here's the deal with this. When we write our compound inequality in set builder notation for and, we have to be very, very careful about this. So what we do is we actually have x is greater than 4 and x is less than or equal to 6. And the way we do this is we use these inequalities, but we list them in order from least to greatest. So 4 is smaller than 6. So here's what's going to happen. And this takes a little bit getting used to. Just trust me on it. If I start my inequality with 4, now notice inequality says x is greater than 4. If I want to rewrite this inequality so the 4 actually comes first, this would be 4 is less than x. Okay, so what I actually need to do here is I need to share the x with the 4 and the 6. And the process is you start with a smaller value. Think about a number line. A 4 would go before 6 on a number line. So I would say 4 is less than x. And now the whole point of doing this is look at this x here. See that the x is now on the right-hand side of the inequality? I can now take that x and attach it to the second part of my inequality that says x is less than or equal to 6. When I'm in class with my students explaining this, I basically say to them like, hey, if I was holding 2 of your hands like this, it would be kind of weird. X is greater than 4, x is less than or equal to 6. But if I swing my 4 around, then I would be in the middle. So that's what's happening, is like you're taking the inequality with a smaller number, you're swinging it around so that x is in the middle. I can hold hands with 4 and I can hold hands with 6. It's a very silly analogy, but when I do that in my class, it pretty much makes it very clear what's happening. Okay, so here's an actual case. It says to participate in Secret Santa or whatever holiday gift exchange thing you might want to do, you must buy a gift that's more than 15, so x is greater than 15, and it must be no more than $25. Okay, so it has to meet both of these requirements. So I want you to make a number line. This is what you would do. You would make a number line that has all of those values there. Sorry. You would make a number line that includes 15 and includes 25. And think about this. All the numbers that are greater than 15 and are less than or equal to 25. Take a look. It is just this inequality. It's just this set of numbers. So these would be all the possible amounts of money that you could spend on the Secret Santa if you were following those rules. In set builder notation, it looks like open brace, x, absolute value, or just that bar really. Now, here's the deal, right? We want to share the x. So if it says x is greater than 15, we want to rewrite it so it looks like 15 is less than x. We flip the entire statement. If I flip that entire statement, okay, the one with the smaller number, then I can attach this x here with the second part of the inequality. X is less than or equal to 25, and that just continues on and finishes our compound inequality statement in that set builder notation. Again, you always look at the two inequalities. You start with the smaller number, then you flip that inequality, and then you keep your variable and basically attach it to the second one. To go on a roller coaster, you must be at least 4 feet tall and less than 7 feet tall. All right, so you must be at least 4 feet, so x is greater than or equal to 4, and less than 7 feet. So now if those are my two inequalities, sorry, I keep moving my screen. Think about it. All the numbers that are greater than or equal to 4 and less than 7. So this would be my inequality here. This is what that graph overlap would look like. All the numbers greater than 4 and all the ones that are less than 7. So ready for the set builder notation. You start with the smaller number, 4. Instead of saying x is greater than or equal to 4, I would say 4 is less than or equal to x. I reverse the whole statement, and then I attach this x with this x here, and it's less than 7. Okay, so now we're going to take a look at the and scenario number 2. So the first one we had is where you have an and statement, and they're going in opposite directions, and the overlap, that section there in the middle, is what we care about. But there's a different scenario, number 2, that we're going to take a look at. So if I said to you x is greater than or equal to 4, and x has to be greater than 6. So now and is always about the overlap, guys. Or was about just anything goes, like whatever took over. The whole thing, the whole solution set was the answer. But here, it's about the overlap. So again, I want to show you what it would look like if I was to take this graph and overlap it with the second graph. And is all about the overlap. So notice the overlap just goes from 6 and on. Okay, so in this overlap, which is all we care about, the x is greater than or equal to 4 is actually the one that doesn't matter here, because the overlap would just be this section. This is the section of numbers that meets both requirements. These are all the numbers here that are greater than or equal to 4, and they're also greater than 6. And so in set builder notation, I don't have anything fancy. I just have to list the inequality that meets both requirements. Okay, so now let's take a look at this. It says to get an A in this class, and I did use the same terminology. I just switched some words up from a previous problem. To get an A in this class, your next quiz grade needs to be at least an 80, and it has to be above a 90. So think about that. If you have to be at least an 80 and above a 90, and means it has to mean both. So would an 85 work? Does an 85 meet both requirements? Is it at least an 80 and it's above a 90? It doesn't meet both requirements. It doesn't meet the 90 requirement. What about a 95? Would a 95 meet both requirements? Yeah. So the entire overlap are all of those numbers that are greater than 90. And if you're unsure about what I'm saying here still, so think about it. At least 80 is this graph here. And then above a 90 would be this blue graph. And notice if it's and, we have to care about what meets both requirements. So what meets both requirements is everything that is here. So we solely just care about everything greater than 90. For it to start snowing, the temperature needs to be less than or equal to 32 degrees and less than 30. So think about this one. If I say it has to be less than or equal to 32 and less than 30, it's got to meet both requirements. Would 31 work for both? No, right? 32 wouldn't work for both. Everything below 30 would work for both. So 29 works, 28, 27, and so on. So this is the graph of what that overlap would look like. It's just what takes over the overlap section. And so your inequality is just simply x is less than 30. Okay, I have one last scenario for you for and this is a good one. It says x is less than 4 and x has to be greater than 6. Now, I will PayPal, Venmo, Cash App, whatever it is, anyone who can drop a comment in my comment section and give me a number that is less than 4 and also greater than 6. Give me a number that meets both of those requirements. You can't. It's impossible. Okay, if I overlap these graphs together, if I swing this one down onto this number line, they're not going to touch each other. There's no part of this graph that's in the overlap section. This is actually no solution. So, or had that special situation where sometimes they can overlap and they're going to take over the whole graph. That's when it's all real numbers. For and, if they don't overlap at all, there's actually no solution. So to guide you then through this, because you know what it's going to be, if I said to you, I will eat any pizza as long as it has less than 2 toppings on it and more than 4. You cannot think of any number that meets both of these requirements. A number that's less than 2 and it's also greater than 4. It's impossible. There's no solution. And by the way, no solution on a number line is literally nothing shaded in. Same thing here. Your chances of winning a prize are not great. They're actually impossible. If I say pick a number out of a hat, you win if the number is at least 8 and it's also less than 5. You cannot think of any number in the world that meets both of those requirements. So it is no solution. I hope this video was helpful for you. Thank you so much for watching. Bye.